Hey folks, welcome back to Precalculus. Today we're in Chapter 2, Section 5, analyzing the graph. So we're going to start off by talking about even functions, okay, meaning y-axis symmetry, okay, symmetrical to the y-axis. So a function f is an even function if and only if for every point on the graph, xy, the opposite x with the same y is still on the graph. So if we draw this and we show, okay, symmetrical to the graph, symmetrical to the y-axis graph here, okay, we can see that this point right here, which is -6, 0, exists also at 6, 0. And this point at -10, -3 also exists at 10, -3. Okay, so algebraically to prove if a graph, now this equation is not this graph right here, but algebraically to prove that a function is an even function, all we simply have to do is plug in the opposite x and see if we get out the same y. Okay, so here, this is an even function. Remember, -6 gave us 0. 6 also gave us 0. Okay, the opposite x gave us the same y. So let's see what happens when we plug in the opposite x and see if we get out the same y. Okay, so by simplifying, we know that the absolute value of a negative number is still going to be the same as the absolute value of a positive number. So we can simplify that to absolute value of x. And anything negative that's squared is the same as a positive number squared, and then the -4, there's nothing there changing. So you can see that when we plugged in the negative x, we got out the exact same y that we started with. Okay, so now let's talk a little bit about odd functions. So a function is an odd function if and only if for every point x, y on the graph, the point opposite x, opposite y is also on the graph. So an odd function basically means you're symmetric about the origin. Okay, so let's take our point -6, 0 here from our first graph. -6, 0, the opposite x is going to be 6, and the opposite y is still going to be 0. But take a look at this point right here. -10, -3 is now going to become 10, 3. And every point in between it is going to reflect about the origin. So a simple way to remember reflecting about the origin means reflecting over the x and then again over the y. Okay, or if you want to think about it as reflecting over the y and then again over the x. Okay, so the same proof is going to hold true for the algebraic part of testing whether or not a function is odd. You plug in the opposite x, and we're going to see if we get out the completely opposite y. Okay, so let's plug in the opposite x and see what comes out. Okay, so we know that anytime you cube a negative number, you get a negative number. Okay, and this negative times that -5 is going to make it +5 x cubed. And -x times 8 is going to make it -8x. So you see here that we got out the complete opposite. We started with a -5x cubed, we ended with a 5x cubed. We started with a +8x, we ended with a -8x. If everything is completely opposite, then we know we have an odd function because we plugged in the opposite x and got out the completely opposite y. Okay, now there's 3 questions I'd like you guys to do on your own. Determine if they're even or odd. Remember the same process, plugging in the opposite x and simplifying. You should see an even power and an absolute value and know what to do there. Okay, you're going to have to convert this one to be a cube root of something squared. That should be a hint there. Okay, and the fact that we see something cubed here times something, and then we see another cube root. Okay, cube root of a negative number. You guys should know what that is. You should be able to simplify this one as well. So give it a shot, pause your video, and complete those 3 examples. Okay, let's talk about describing a graph now. So whether a graph is positive or negative. Since x-intercepts have the form x0, whatever x that is, they are often called the zeros of the function. Okay, the zeros of a function that crosses the x-axis separate x intervals where a function is negative from where the function is positive. Basically meaning, is it above or below the x-axis? Okay, the graph is positive in quadrants 1 and 2. 1 and 2. Okay, where the graph is above the x-axis, like I just said. The graph is negative in quadrants 3 and 4, where the graph is below the x-axis, like I just said. So let's talk a little bit about increasing and decreasing and constant. So when we read a graph to determine if it's increasing, decreasing, or constant, we look from left to right, just like we read a book. Left to right. So if a graph is increasing from left to right, it'll be going up. If it's decreasing from left to right, it'll be going down. If it's neither, it may look something like this. A flat one would be constant, and so on. Okay? Now let's talk a little bit about maxes and mins. So a global max, also called an absolute max, is the largest range or y value over the entire domain, or all the x's. So what is the biggest y value on your graph? A local max is called a relative max. Relative max that gives the largest range or y value in a specified interval, or in layman's terms, a window. So over a small interval, what is the biggest y that you have? And the same holds true for minimums. So there's a global or absolute minimum, which is the smallest range over the entire domain, and a local min is a relative min, which is the smallest range over an interval or in a small window. So an endpoint maximum can occur at the endpoint of a domain. For example, you have something like this. That point right there is an endpoint maximum. And the same definitions apply to locate minimum values, like I just said, for the local range. Local, relative, absolute. Everything applies. The same way we did maxes, the same thing applies to mins. Okay, now we're going to talk about end behavior. We're going to do these things a little bit differently to kind of get you guys ready for calculus. Okay, so the end behavior of a graph is the direction that the end is pointing. Okay, so we look at the left to right ends toward negative infinity or positive infinity to determine if it is pointing up or pointing down. So from an equation, you look at the degree, meaning the largest exponent, and the leading coefficient. Leading coefficient, meaning the number in front of the variable with the highest degree. Okay, so this end behavior is often called the leading coefficient test. Okay, and to do that, we're going to start exploring infinite limits. Okay, so an infinite limit, okay, written as LIM. Limit to you means height. What is the height, or the y coordinate? Okay, so when we see this notation right here, the limit as x goes to infinity is basically saying what are the y coordinates do as x approaches infinity, as x goes off to infinity. Okay, and you'll often see a function in there, I'll just write f of x. Okay, so the leading coefficient test, an even degree function, something squared, fourth power, sixth power, eighth power, so on, with a positive leading coefficient is going to look something like this. It might be a parabola, might have a dent in it, whatever. Okay? The limit as x goes to infinity of this function. So as x goes to the right, what is the height doing? The height is going up towards infinity. And the limit of this function, the height of this function as x goes towards negative infinity. Meaning as x's go left, what's the y-coordinate doing? Well, the y-coordinate is still going up. As we go left, it's going up to infinity. Okay, so what I'm going to have you guys do is I'm going to draw each one of these next three, but I'm going to have you guys evaluate the limits. So if a function is an even degree with a negative leading coefficient, it's going to flip this U-shaped graph upside down. So it may look something like that. Now you need to evaluate both limits. If it's an odd graph, an odd degree like x cubed or x to the fifth or x to the 11th, whatever that may be, it's going to be S-shaped, and because it has a positive leading coefficient, it's going to be a forward-facing S. So you should be able to evaluate both limits. As x goes to infinity, graph's going up, and as x goes to negative infinity, your graph's going down. And lastly, you probably guessed it, if your function has an odd degree, it's going to be S-shaped. But if it's negative leading coefficient, then it's going to be a backwards S of some kind. There may be extra humps in there, it doesn't matter, but the overall shape will be S-shaped. So go ahead, take a second, pause your video, and evaluate all of the limits of each function as x goes to infinity, and all of the limits of each function as x goes to negative infinity. Then pause your video, take a second, get the next 6 limits done. Okay, so I'm going to do one of these next ones with you, and then you guys are going to do the last 2 on your own here. But we're asking about what is the end behavior. So what is the infinite limit of this graph? So let's look at this first one. It is an odd degree, x to the 7th power. The highest power is 7. Okay, meaning it's going to be one of these, it's going to be S-shaped, and the leading coefficient is positive 1. So I know that it's going to relatively look like this. So it's going to look something like that. So now I can evaluate what is the limit of my function as x goes to infinity, and I can evaluate what is the limit of my function as x goes to negative infinity. So as we go right, as the x's go right, my limit or my height is going up towards positive infinity. As x goes to negative infinity now, as I go left, going towards the left, going towards negative infinity, my graph is going down to negative infinity. This one should match what you have up here. Now, I want you to take a second, pause the video, and do these next 2. Now, I will caution you, you see a negative leading coefficient with an even degree. And over here, you might be tempted to see a positive leading coefficient with an even degree, but remember, degree is the highest exponent, which is right here, and has a negative leading coefficient. So pause it, give it a shot, and check your answers in class. Okay, let's take a look at this last example here on this page. And they've given us a graph. We don't need the equation. It's just a function. It passes the vertical line test. And we're being asked to find the domain. So the domain, remember our vertical boundary lines? There's nowhere where this graph doesn't exist. So the domain in interval notation is negative infinity to infinity. The range, remember, is our horizontal boundary lines. So it looks like our range going from bottom to top starts at about negative 4.5 and goes up forever from there. So we're going to call our range negative 4.5 to infinity. Okay, now let's take a look and see where is this graph increasing. Remember, we read increasing left to right and using our x values. Okay, I like to imagine when I think of increasing and decreasing that it's a little roller coaster. There's a little roller coaster. There's a little guy riding the roller coaster. So increasing, when is he going uphill? Decreasing, when is he going downhill? And then constant would be anywhere he's flat, and I don't see anywhere he's flat. So increasing, reading left to right. Okay, well, he starts off over here at negative infinity. He's going downhill until we get to right here at negative 3. So at negative 3, he starts going uphill all the way to 2. All the way to 2. Now, I'm going to always use parentheses with increasing and decreasing because at the bottom of a hill or at the exact top of the hill, we are neither increasing nor decreasing. Okay? The slope of our tangent line, the slope of our line tangent would be 0. So we are neither increasing nor decreasing. Okay, so let's see. After he does that little part of the hill is going uphill. Now he's going downhill. Now right here at 5, when x is 5, we would start going uphill forever. So we're going to union with 5 to infinity. So now let's take a look at decreasing. We don't see any flat parts when there's no constant parts. So basically, if there's no flat parts, wherever he's not increasing, then he has to be decreasing. He has to be going downhill. So from all the way here at the left, negative infinity, all the way to negative 3. We're decreasing, and we start to go uphill. We already talked about that. And then right here, this little interval right here, okay, from 2 to 5, we're going downhill. So from 2 to 5, we're going downhill, and then he starts going uphill forever again. And it should make sense that these are kind of filling in the pieces. So from negative 3 to 2, he's increasing, and notice there's a hole from negative 3 to 2, and the decreasing interval, and so on. So let's talk a little bit about maxes and mins. Okay, so the min. We have a global min right here at negative 3, negative 4.5. And we have a relative min at 5, negative 2.5. I'll point to it right now, right here. Now let's talk about maxes. Now there is no absolute or global maximum because the graph goes on forever. Any maximum you give, we can always find something higher because the graph goes forever high. But as far as relative max, we see we have a relative max right here where I'm shading. Relative max at 2, negative 1.5. Okay. Now let's talk about where is our graph bigger than or equal to 0, or where is it less than 0? Basically, where is it above the y or the x-axis, and where's the y above the x-axis, and basically where is the y below the x-axis? Okay, so let's talk about above the x-axis first. So basically everything to the left all the way up to right here where my pen is, which looks to be about negative 5. So from negative infinity to negative 5. And I'm going to include it because we want to know where it's greater than or equal to 0. So it's equal to 0 at negative 5. Okay. We also notice that our graph goes above the x-axis again right here at 7. So we're going to union with 7 to infinity because all the way to the right, our graph is above the x-axis. Okay, which should make sense to you now that everywhere between negative 5 and 7, as we can see on our graph is below the x-axis. And notice I'm using parentheses because we don't want it to be equal to 0 here. We want to know where is it less than 0. Okay, last question here. We're asking whether or not is this function even, odd, or neither. Well, if it's even, it should be symmetric to the y-axis, recalling back in your notes. If it's odd, it should be symmetric to the origin, meaning reflected over the x and then the y, and you'll get the same thing. Well, I don't see it being symmetric to the y-axis, so it's not even. If I reflect it over the y-axis and then the x-axis, I'm going to get an upside-down U-shaped graph, so it's not odd, meaning it has to be neither. So right now what I want you guys to do is to apply all of that and see if you can get this one done on your own. And we can talk about it in class as well. Bring your questions to class. I look forward to helping you.